For the second talk of the day, we have basically Matessi from Milano, talking about the content fibration on Calabi-Yau.
Thanks, organizers for this conference. Very nice. I was here in Miami last time 10 years ago, maybe or more. Similar conference. Nice to be back and to see how much things have progressed. Some of the things that we talked about this conference, but I was here were just maybe vague ideas, and now they have developed things. Yeah. So now what I want to talk about is the construction and the still work in progress, hopefully almost finished, of Lagrangian fibrations on Calabi-Yau hypersurfaces. And it's joint work with Ilya, Chekiu, and Helge Ruda. So this, in fact, will be just the first part, and then there will be Ilya and Chekiu explaining other part. Okay, so today, so in this talk, I just want to give an idea of the main ingredients of the construction of these Lagrangian fibrations. So I start with the setup. So what we start with a pair of dual reflective polytopes. In our n+1. And then what we do, we choose some, well, this is an assumption, you can't always do this, but we assume that there is, S is central unimodular triangulation of the boundary of P naught. So that we can construct the fan consisting of the elements in this triangulation. So the fan sigma S is just a set of cone sigma, where sigma is an element of this triangulation S. So it's the fan, and you take the toric variety corresponding to this fan. That toric variety corresponding to this fan. So what this is just so this fan here, sigma S, is just a special refinement of the normal fan to P. So this is a refinement of the normal fan to P. So this toric variety is in fact a frequent resolution of the toric variety associated to the polytope P. Okay, so the Calabi-Yau hypersurface we consider is in Z, is in this toric variety, and it's just an anticanonical smooth hypersurface. So X in Z is an anticanonical smooth hypersurface. So in particular, it's Calabi-Yau. Nice. And it's of dimension n. Okay, so
for how long is it to be this stuff?
Sorry?
C is smooth.
Yeah, it's a smooth because we assume that we can do this. That we can find a central unimodular triangulation of the boundary. So it's a smooth. Okay, so in particular, we can write x. So actually, so if we take the big torus orbit, instead, this is the big torus orbit. We can write the x inside of this big torus orbit with this equation. With some equation of this type, with some coefficients to CA, z to the A is equal to 0, and where these exponents A are in P intersect z to the n plus 1. So that's the equation in the big torus orbit of X. Okay. So, okay, so now, because we are constructing Lagrangian vibrations, so we're in the symplectic world, I have to specify which symplectic form we are using. So in fact, I should have added here some other hypotheses saying that this is regular central unimodal triangulation, so that Z is actually projective toric variety. So it means that there is that omega be a toric Taylor form on Z. Okay, so okay, then I state the theorem. This is what we prove. So so it would be this. So that there is this a Lagrangian vibration f of x to some base b with the codimension 2 discriminant. Okay, so discriminant is the set of singular fibers on the base, the set of points on B that corresponds to singular fibers here. And yeah, okay, so this is the statement. And let me say a few things about the base B. So the base B is actually a priori it's just a topological manifold. It doesn't have it doesn't have a natural smooth structure on it, but what I can say is that if D is the discriminant, let's say that P is the discriminant locus of this vibration, let me say that on B minus D there is a natural smooth structure as a natural smooth structure. And the F restricted to B minus D is the smooth. Okay, we cannot say much more than this concerning the smoothness of this vibration. Well, the natural smooth structure is just given by action angle coordinates on the base. Perhaps Ilya maybe would say something more about this. Okay. So now I want to explain a little bit what are the main ingredients in the main and keywords that appear in the proof of this theorem. So are there questions so far?
Yeah. So if you modify the coefficients, you can degenerate to the boundary division. So does the topology of P coincide with some dual convex of the boundary division?
Yes, I think, yeah. In fact, you can think of it as the
If you remove the word
as-
you,
yeah, you can think of it as the boundary of not of P, not the boundary of P, but the boundary of the moment polytope of Z.
The second question, I assume that the Fermat quintic is one example of this situation.
Yeah, the quintic.
And then I had a look to your paper with Castaño Bernard, and then the discriminant was a thickening
Yeah.
of a graph.
In this case, it's actually the graph. It's
It's the graph, but without the thickening.
without the thing.
Thanks.
But it's an improvement in that sense because that's what I mentioned too. Okay, but yeah, but we don't know about smoothness. Not even along the graph. We don't know about whether this method is smooth also because of the construction, because the way it's constructed.
And I think it's important to say that the singular fibers are n-dimensional.
Yes. Yeah, the fibers are full dimension. Yeah, and
It's
dimension.
not higher than it's exactly half the
Full dimension. Full dimension. Well, see, you have the full dimension for a Lagrangian thing, for isotropic. Okay. Yes. Okay. So what are so let me say a word about the stage. One of the ideas, I mean, the main idea is to modify this equation in order to break X into some local models. So I just want to say what the local models are. So local models of type K and D. So they are just these varieties. A local model of type K and D is something, a variety of this type. So you consider this equation, x0 times x1 times xk equal to 1 plus w1 plus wn. And then we look at this as something inside t to the k plus 1 times c star to the n times c star to the d. Okay, so now here is where the x live, here is where the w live, and the remaining ones are just the free variables that don't appear in the equation, but it's important that they are there. And so that's a local model of K and D type. And let me say a few properties of this local model. It has symmetries. So there's K plus D, let me say Hamiltonian torus action. So there's a TK plus D torus action on this variety, which is simply the torus acting on the variable. So we have the action of the torus on the variables, and you consider the torus that preserves this equation. So you have a TK action which preserves these variables, this monomial that preserves this monomial, plus the TD action that just simply rotates these variables that do not appear in the equation, but they preserve the local model. So now it's important to say that this full torus is well defined, while the TD torus action is not precise, well defined, but this will be important later, maybe. Yeah, well, you can take the standard symplectiform that you see here and here. I don't.
What do you mean that he's not well defined?
You'd have to take.
You say that there is some sort of like monotony.
Yeah, how do you see that TD is not well defined here? Because
Splitting is not well defined.
yeah, this splitting
This
here is not well defined. Yeah, this
splitting
splitting.
is not.
Yeah, it's not defined. So the way to define this torus, the full torus, you take the orthogonal to this monomial. So you take the orthogonal to 1, 1, 1, 1. I mean, you take the orthogonal to the space spanned by this monomial and these monomials here. Okay, you take the orthogonal to that, and it preserves, and this is that torus. Okay, but okay, so now. Okay, so now, yeah, the keyword for this. So these local models have been around since the early days of, as I said, conjecture, because yeah, they admit torus vibrations which have the right topology. You construct topological torus vibrations on Calabi-Yau, but it's difficult to construct a Lagrangian vibration on this local model. So they have nice topological vibration on it, but constructing an actual Lagrangian vibration on these local models is difficult. And what we now know how to do is construct a Lagrangian vibration on these local models, and it's via Lagrangian vibration via Evans-Mauri type Liouville flow. Evans-Mauri type Liouville flow. Right? That's or we now know how to do it, and this will be explained, I think, by Q will explain how to do this, construct Lagrangian vibration with an Evans-Mauri Liouville flow here. Evans-Mauri invented this method. Mauri, sorry. And we are adapting it to this local model. Okay. So now so now what I want to explain is I haven't said it. Okay, so there is a topological vibration on here, which I don't want to write down, but I haven't said how to construct what's the Lagrangian vibration here. It will be constructed by this method. It is constructed by this method, but I haven't said how. To explain by Q. So it's just to say why now. Because now I want to explain how to break up X into this local model.
So you can't easily write it down.
No.
It's a theorem.
It doesn't have an expression for me. Yeah. It's in fact it will be defined not as a map, but as a foliation. So there's not an explicit map, at least that you can write down in formula. Okay. So now. So now let me explain scalar potential. This is another ingredient which is important. Okay, so now since we are, so I told you, I mean, a toric variety has this big torus orbit, C star the n plus 1, but that's see in this big torus orbit you see the complex structure. But how do you see the symplectic structure? Because that's what we want to work with. Okay, so now so let mu from Z to Q be the moment map of the n+1 action. As I said, at Z we have picked on Z toric Taylor form, so it means that Z has a Hamiltonian T n+1 action, and Q is the moment polytope. So if P, okay, so what's Q? If P was smooth, you could choose some Taylor metric where Q is equal to P. Okay. Otherwise, if P was so smooth, Q looks almost like P in the sense that it's combinatorially the same, but maybe it's stretched in some direction. Or, otherwise, Q, if P is not smooth part of Q will be something which is a resolution, so with angle cut. Okay, so now, what's the symplectic form? So if we, so we have that T star n+1 is the big torus orbit, as I said, and what's the Taylor form on there? Well, there's a symplectomorphism. Symplectomorphism to what? To Q, the interior of Q. So let me write interior of Q like that, times R n+1 star modulo Z n +1 star. Okay, that's the torus. So I'm writing it as the dual because so if Q0 lives in Rn+1, the torus is the dual. So let me take coordinates P here. So P are the coordinates on Q. Say Q0, Q is in Rn+1, and the theta are the torus coordinates. So the symplectic form is just the standard symplectic form, which is dpi which d theta I. So that's symplectic form. And what's the symplectomorphism like? Or better, how do you see the complex coordinates on this description of the big torus orbit? How do you see the complex coordinates? So you need Taylor potential. What is it? Okay, so let me describe the Taylor potential that gives the complex coordinates there. So first, you describe Q in this way. Q is a polytope, so it's described by inequalities. In particular, it's described by a set of inequalities of this type. No, bigger than. Bigger than. Oh, sorry. Bigger than Q. It's smaller. No, bigger than. Well, it depends on how. Yeah, let's put it bigger than Q. Okay. So these are a set of inequalities. You can think of these EI as being the rays of this fan. So EI are elements of the triangulation, are vertices in the triangulation that I showed. Okay, so and now, okay, so now let me call these functions here V. VI are these functions. So they are just okay. So now take P. Let P from Q to R be a smooth, but from the interior actually of Q, smooth, strictly convex a function of the type p equal 1/2 the sum vi log vi plus p0, where p0 extends to a smooth function on Rn plus 1. So if phi is a function of this type, it's called a scalar potential. And the point is that you can define complex coordinates in this way. You can define complex coordinates in this way. Zi is equal to e to the partial derivative with respect to xi of phi plus I theta I. These are the complex coordinates, and so you can plug them into the equation of Z. So equation of x of x becomes sum a in p dA z to the differential phi of like a plus I theta a. Oh, sorry, e, sorry. Yeah, it's the coordinate on the Rn plus 1. Yeah.
The x size of the coordinates of n plus 1 of the I that expression of the I that defines the function.
Yeah, x. Yeah, yeah.
X.
They're the linear coordinates on the polytope.
Yeah, vi is a function of the x. Yeah, sorry. I used the same I. Sorry. Let me call this k. K and k. What I mean is dk d is d phi by dxk. But locally, you can also use the vi's as coordinates, and then it will become. You just have to also change the theta, but that's okay. Okay, so yeah, so this is x, right? And these coordinates extend to the boundary, and so they also this thing here compactifies to the actual toric variety corresponding to Q. Okay.
Can you maybe switch the marker because it's
Sorry. Yes. Sure. Right. Do you need to write something this better, or will be good?
oh, it's okay.
Yeah. So this is the. Yeah. So let me just also write a diagram of this. So we have this. What is this? So we have this Q times this torus Tn plus 1. We map it to C star n plus 1 in this way. So this what I wrote here gives a map from this to this to C star n plus 1. And here we can map it down via the log. We take the log of the modulo of each coordinate. It goes to R n plus 1. And this map here, this maps to Q. And this map is just a differential of phi. Okay. And this the differential, yeah, of phi. Okay. Question on this. This is classical. I mean, maybe I think Abreu Liouville. I think. Okay, this. Okay, so now I want to explain the idea for the proof of the theorem or of the construction. Now I want to take a special form of this equation, of the algebraic equation. I want to take a special form of this equation, and I do this by something which is common in tropical geometry. In fact, it's the beginning of sort of Q. Sorry? Oh yeah, it's interior. Sorry. Yeah. Yeah, it's here. At least, yeah. The differential of the is the number. Okay. So now I want to take an equation which is what we usually do in tropical geometry to write this. So let's take also T a triangulation of delta P now, of delta P. And then take the cones, and then take the central triangulation induced by this, central with respect to the unique interior point. And so we assume that this triangulation T is induced by a piecewise linear eta from P to R, which is also integral, as we usually do. Okay. And then write X, so algebraic equation for X. Let me write it already in that form with the potential there. I'm just telling you how to choose the coefficient here using this eta. So, also, yeah, for always A in P, you also write it in this way. Actually, A in the boundary of P, minus eta A times S times E, and this would be just the same thing. So, equal to E3S. I write it. Now, okay, so these are just simply the coefficients. This stays the same. These are the coefficients CA in this special form. This is little s, and this is big S, and these are two parameters. S, little s, and big S are parameters which we need to take big enough. So we have to think these as big parameters. Okay, that would be the algebraic equation. And now the idea that I want to explain is so idea to break, let's say break X into A and the local models. How to do this? Well, change the equation, replace the equation with, so I don't want to write it again, but I just go back here and I'll tell you how to replace the equation. What you do is put here you put some cutoff functions. Well, let me write that into row A. These are some cutoff functions which I'll explain better now, in a while. And then you also change this. We also change phi. We don't use the standard Kähler potential, which is strictly convex. We also change this. So now this is the equation we work with, and now I want to explain how to choose these cutoff parameters. So these cutoff parameters are functions from Q to R. Well, yeah. Let's say cutoff functions which have the property of killing. They become zero, so that you kill some exponents, some monomials here get killed by this row A. And this you see here that we also change P is blue P. Is a new potential, not even a real potential, in the sense that it's not a Kähler potential, which is only convex, not strictly convex, and has some linearity. Some linearity, which are very important. In the sense, has some linearities in the sense that it's convex, but it won't be strictly convex because it's linear in certain directions, which are carefully chosen. That will do the job. Okay. So now I want to spend a little time with a drawing to explain how P and rho are chosen. I'll try to explain it with a picture, with a low-dimensional picture, just a two-dimensional one, but I hope it conveys the idea on how to do this and what it does. So the cutoff functions are not really new. They've been used a lot in the previous literature. Like, for example, I think Musaid used them to filter coefficient. But yeah, our input here is this non-strictly convex potential. Now let me try to explain. Okay, I have 10 minutes. Yeah, okay. So let's take one two-dimensional reflexive polytope. Let's take 3 times the standard simplex in R2, and which looks like this. Well, it's lengthy. Each edge has length 3, so there's an interior. There's an interior point there. Let's look at just this corner here, which you assume that it's triangulated like that. So as I said, we have chosen the triangulation E, which is induced by this eta. So eta bends here. Okay. Now, if you do
The triangle should be a piece of the boundary of P.
yes, you triangle. In this case, you only have one choice. Oh no, you have more choices. Yeah. Okay. So you triangulate the boundary, and then you take the cone. So the triangulation on the boundary is just you subdivide each edge, right? And then you take the cone. So what I've drawn here is not it's the cone over P. Okay, the cone over there. What? Oh, eta. Oh, no. This is, sorry, not from P. So I was, yeah, it's from P. Yeah, P. And so P is the polytope. I'm assuming here that this is P and it's also equal to Q for simplicity, right? So eta here, this eta here is piecewise linear. So it's linear on each of these triangles, but it can bend. And it's convex. Okay, so what one does in tropical geometry, you can draw on the other side, on the dual side. So this is in Rn plus 1. In Rn plus 1 dual, you draw the tropical curve corresponding to this subdivision eta. Then you just draw a piece of this tropical curve. Let me draw it in big. Okay, so that's the piece corresponding to this. So this point here is the gradient of eta along this triangle. This point here is the gradient of eta on this triangle, and it's joined by the dual to this edge. So that's the tropical curve on the dual. And so far this is standard, but now what we do is do a further subdivision of this triangulation like this. We take the dual subdivision, sorry, not triangulation. We do the dual subdivision and we add this bit. So we have the green one plus the black one. So then you construct a new function, which is somehow, which we call eta tilde, which also bends along this green line. So it's still convex, and it also bends here.
In which sense they give this a triangulation?
This is not a triangulation, it's a subdivision. Subdivision, yeah. It's a dual subdivision. And you find eta tilde that induces this subdivision. Okay, convex still. This is called the push construction. Well, we call it the push construction. Okay. I don't know exactly why. I
So you
didn't
push
invent
it
the
and
name.
you push the base, you take the function and then you push the body center so it will be lower than that.
Okay. Now what's the corresponding dual thing to such an object? It will be something like this. It will be, you get some triangle here. Oh, sorry. Some triangle there. Like that. So now the dual object to that is the blue curve has disappeared. You don't see it anymore here in the dual description. You just see this black thickening of the blue tropical curve. Like, what are these two triangles here? This one and this one, they're just dual to this point and to that point. What's this rectangular region here? It's just dual to this point here. Okay? Okay, now consider this is a piecewise linear function, eta tilde. Now consider like a smoothing of this eta tilde. That means you just round off a little bit the corners of this so that it becomes smooth. Okay, now P, this P here is now a smoothing of eta tilde. Just a little smoothing that rounds off the corners. And it would be convex because eta tilde was convex in the start, but it won't be strictly convex. Now what does the differential? Now we look at this differential of phi. The differential of phi will be a map. dphi will be a map from this picture to that picture there. What does it do? Now you consider a little neighborhood of, say, this point here. It will be convex in that, strictly convex in that little neighborhood, and the differential will fill up this square. You take a little neighborhood of this point, the differential will fill up this triangle, and so on. So the image works like that, the image of dphi. So that's how dphi looks like. Now the rows. The rows are like this. So you have one row for each coefficient. This is a coefficient, A. So it's one of the exponents. This coefficient here corresponds to some region over here in the dual picture. So let's take, now I'll draw this. You look at this region, which we say, call it HA. I draw it a little bit bigger than the region in the blue line, because now I want to say that this region here is the support of this row A. So row A will die outside of this green region, and it will be one basically inside this region, except maybe a little bit on the bottom, right? So it's one here, and then it slowly dies and becomes 0 over there. Similarly here for this other coefficient, A prime, right? You have a row A that has support here. So it means that now there will be, let me draw it like this, a region here corresponding to the complement of this green region. So corresponding to this region here, where the coefficients corresponding to, where you don't see, where the coefficients corresponding to this monomial and to this monomial have died. The only ones that survive are this one and that one. The only coefficients in this equation that survive in this region are this coefficient and that coefficient. So if this is the origin, say, if suppose we have chosen the origin here, then this is 1, 1. What's this equation? What is this equation?
The A is not carrying on the boundary of B.
Sorry?
But now it varies on the boundary of the refined triangulation.
Yeah. So true. In fact, this is not precisely. This picture here does not correspond exactly to what we do. So.
But the origin is moved to the right hand side.
Yeah.
There is a right hand side.
Yeah, I moved the origin. It's not the
origin.
Yeah. But
the monomial which corresponds to the origin is over there. It's not cut off. It's always on the right side. So we only cut off the monomial so far.
yeah, you can put, yeah, exactly. So you can put some monomials near the boundary. You can put some of the monomials over here. Okay. But so if these two monomials have died, what's left here is these two. And what does this equation correspond to? Well, it corresponds to x times y equal 1. Right? So when you do this, you're only left with these two monomials, which correspond with, in this region here, you're left with these two monomials, which correspond to this equation, which is one of the local models. This is the local model of type 1, 0. Okay, so, right, and what happens like here? Well, around this point here, you have like just 3 monomials survive, because you have the monomial corresponding to this region and to this region have survived. All the other ones are killed. So for in the neighborhood of this point, the equation will have like this monomial, that monomial, and that monomial. So we get the other equation. and so on. So this is the idea of what this potential does. There are problems in the sense that what we want is that this thing to be symplectic, right? If T was convex, it would be symplectic automatically because it's holomorphic on the other side with respect to Kähler form, and holomorphic submanifolds are symplectic. But one has to prove symplecticness in this case, and that's a bit of work. And yeah, maybe Ilya might maybe say something about this, or should I? I think I ran out of time.
Can you prove that it's kind of like symplectomorphic for complex X?
Yeah, that's what we
Work.
Yeah, that's what we have to do. So once you prove that this is symplectic,
Then there's a family.
then you can deform it to a family to the holomorphic one, and then it's the second one. To the holomorphic.
Is it like inversion with that? Maybe I follow like what's like significantly different from like
It's the Paso numeric. Yeah.
It's not a complex manifold. That's the key difference.
but doesn't he show that his thing also generates like these
So the reason why
Yeah, but
we
there's no Lagrangian vibration.
yeah, no Lagrangian vibration.
Yeah, but in terms of conjecture, it's very close. Because
so yeah, I have to say that I didn't explain why this thing is good. So it's good to have these linearities because when we do the Liouville flow, and this will be explained by Q, but when we do the Liouville flow, these linearities guarantee compatibility between different local bonds. So that, yeah.
It also gives the action.
The linearity don't come just from the local equation because
Yeah,
if you break it up into
Yeah, you have the local equation first.
yeah. But the thing of the linearity is essential for having the Liouville flow technique to work compatibly at different local bonds. But if you will say, okay, sorry.
That's thank you, speaker.